I'm Mike,
and this is our Fetal and Placental Growth Project.
So, basically, the objective of the project was to look at this graph and kind of determine what it means. So, this is a graph that was reported on by Forbes, which was a study on fetal and placental growth rates. So something that I really want to point out here is that the fetal growth rates, which are colored in black, they are much more numerous than the ones that are colored in white, which is going to be the placental growth rates. And so this is an important topic just because placental ends here and fetal ends all the way out here. We're going to touch upon what that means later in the presentation, but for now, just keep note of that.
Okay, so in order to continue with the project, we first had to interpret the graph and find out what form it's in. Our options could either be a normal function, the first derivative, or the second derivative. Okay, the first thing we need to look at when we are determining what form the graph is in is the units on the axes. On the x-axis we have weeks, and on the y-axis we have grams per day. This is our first hint that this graph is in the first derivative. Another hint is our explanation of the graph. It tells us this is the velocity of growth. Velocity also means the first derivative, which is another hint that it's the first derivative form. If this graph was in the normal function, the y-axis would have just a label of grams, and if it was in the second derivative, the y-axis would be grams per day squared, and velocity for a normal function would just be a weight, and for a second derivative, it would just be acceleration.
From the previous graph, we came up with two of our own graphs, one for the fetus and one for the placenta. As you can notice, the graph from the original and these two new graphs changed. In this graph, we used days because it was easier to collect the data using days. As you can notice, going back to the original Forbes graph, the fetus grams per day and the placenta grams per day are at two different rates. One is going from 0, 10, 20, 30, 40. The other is going from 2, 4, and 6. We had to take this into account when separating the fetus and the placenta into two different graphs. By analyzing this graph, you can realize that the fetal graph ends at around 440 and the placenta graph ends at around 260 to 270.
So as you can see here, we decided that our next course of action would be assigning a line of best fit. So we initially assigned a line of best fit with a polynomial degree of 1. So as you can see here, there's a line of best fit here, a line of best fit here. This is fetus and this is placenta. So we also got out of these the equation of this line, and we've got the r squared values. So as you can see, the r squared value for the fetus and the placenta are both relatively low. This means that any value we get out of these lines of best fit is going to be met with kind of low confidence. So we had to change that. So the next thing we did was kind of correcting that to try to get a bigger r squared value to get more confidence.
The next step was to find a new best fit line using a polynomial with a degree of 4. As you can see over here, we have the fetal and placenta equations for this polynomial, and they look very long and complicated, but this is only because we changed their values to 10 decimal places, which causes for better accuracy. When comparing these two r squared values with the ones with the polynomial degree of 1, we can tell that they're bigger, and as the r squared value gets bigger, the better the fitting is and the more confidence we have in our final numbers.
Now that we found a trustworthy equation for the first derivative, we can use that to find a trustworthy equation for the second derivative. In order to find the second derivative, we used the first derivative and took the derivative of the first derivative. After we found the second derivative, we used the second derivative and plugged it into decimals. We plugged it into decimals to get the inflection points. The inflection points are when the graph of the second derivative crosses the x-axis. The graph of the second derivative crosses the x-axis for the fetal weight at 118, 284, and 419. It crosses the placenta weight at 116, 195, and 250.
So what does any of this mean? What is even happening right now? Well, what we just found were the inflection points. And so the inflection points for the fetus were 118, 284, 419. The inflection points for the placenta were 116, 195, 250. So the significance of this is just because, well, first off, we have to narrow this out. We have these two, 118, 116, and we have these two, 419 and 250. The range that we're given in our data values, this is basically right at the edge. So we don't think these are very significant at all. There's just too much there's too much potential for error here. But the middle, the 284 and the 195, these inflection points could tell us something very, very important. So with the fetus, this inflection point is 284 days. So if you did the math, that's 9 months basically. And 9 months people usually pop out a baby. So what this could mean is that at this point, growth starts changing. And so if we looked at the graph, which we'll get to a little later, at this point, the growth starts increasing at a decreasing rate. So at this point, we're still growing, but we're growing at a much less rate. And so for this point right here, 195, if you did the math, that's about 7 months. So at this point, the baby's not born yet. So it raised a couple of questions. Why is this placenta growth changing right here? And as with before, it's going to be increasing at a decreasing rate at this point. So a couple theories that we had. One was that the baby, it just doesn't need the placenta as much at 7 months. Maybe it starts producing its own hormones or nutrients, and it doesn't need the placenta as much, so the body starts putting as much into it. Another theory that we had was that maybe the body, since it's about to give birth and lose the placenta and the baby, it just starts to not put as much into the placenta. Because why would you put so much energy into growing up this placenta and then immediately have it lost? So that was basically what we thought with these inflection points. So let's move on.
Our next step was to find the antiderivative, and in order to do this, you need to take the antiderivative of the first derivative. And this is the process shown on the board, and in our project we were given that at 112 days the fetus weighed 100 grams and the placenta weighed 120 grams also at 112 days. So we needed to find C, and in order to do this we plugged in 112 for all the T's and we set it equal to 100 for the fetus and 120 for the placenta, and we found C. Now that we have our C values, we can plug them into the equation, which we can then plug into Desmos, and we get our graph for the weight of the fetus and our graph for the weight of the placenta.
Basically what happened at this point was we got a new set of values. And so this set of values was basically plotting in gestation placental volume instead of what we were plotting before, which was placental weight. So we immediately identified this as a primary function, not a first and second derivative. And the reason why we did this was because it was just simply measuring the volume. It wasn't going to measure the rate of how quickly the volume was changing or the acceleration of the speed of the volume. It was just nothing crazy like that. It was just measuring, this is how much volume is there. So this is a regular function. So what we did was we basically took these values and we made a graph. And so by plotting these values. And so after this, we took a time of 0. We took this and we decided, well, we want to plot it based on this equation that we got from this line of best fit. We want to plot this. So we took this 0, we plugged it into the equation, and we ultimately got, when t is 0, the volume of t is going to be negative 2,200, who cares? It's negative, that's bad, because you can't have a negative volume, so that's impossible. So we were at a bit of an impasse here, we didn't really know what to do. But what we eventually figured out was that we were given weeks of gestation from week 20 to week 40. So what we can basically do with this is if we pick a number inside of 20 and 40 in that range, we can get a value that we have a reasonably high chance of predicting, like around whatever, we're going to get like a reasonably accurate volume if we pick something inside the 20 to 40 range. But what we did was we picked something outside that 20 to 40 range. We picked 0. And our equation just isn't fit to handle that. So if we wanted to fix this problem, we would probably have to include weeks that include 0. So if we measure this from 0 to birth, basically, if we measure this from week 0 to whatever week would be month 9, I don't know. That would include this value, so we could have a reasonably accurate chance of plugging 0 into this equation and getting an accurate volume. So now that we found this equation for the data for the placental volume, we can now move on and try to find the inflection points to try to compare them to the placental weight to see if there are any similarities that we could draw. So the important thing to realize here that we already discussed just previously was that this is the regular function. It's not a derivative. It's not a first derivative. It's not a second derivative. So to find the inflection points, we have to find that second derivative. So if we want to find the second derivative, we have to take the derivative twice of this equation. And so we did, and so we got the inflection points, and so they're going to be 203 and 273. And so we can compare them to the inflection points that we have for placental weight, which is 116, 195, and 250. So what could this mean? So something I really want to draw your attention to right here is these two. There are two kind of thoughts that we could take out of this. One that says it really doesn't mean anything, and one that says it does mean something. And so to us, we think that this has some weight just because right here, we already judged that the placenta is going to start increasing at a decreasing rate rather than from here to here where it's increasing at an increasing rate. So right here, it's going to start increasing at a decreasing rate. And so we see right here, there's a change in inflection here, which is very, very close. I mean, it's only a few days off. It's basically a week off. So you could say that because that there's like this change in inflection here, right when placenta weight starts going down, and right when placenta weight starts like increasing at that decreasing rate, you're going to get the volume start to increase at a decreasing rate as well. And the volume is obviously going to contribute to the weight, so that makes sense. So you could also possibly say that you can't really compare the two just because they're different units, they're measured in different ways, and they're from different sources of information. You could also say that too. But if you cast that bias aside and you just look at these two, you could draw a connection here. So while the information sources are different, there could be a possible connection.
Now that we have all of this information, do you trust this data?
Although these two graphs for the placental weight and the placental volume are from two different sources, we do trust the data because of the two significant events occurring around the same time, which is around 7 months.
What significant events occurred at month 7?
So at month 7, we had placenta changes, and so that was where the inflection point for both placenta volume and placenta weight changed to indicate a increasing at a decreasing rate. And so this was very important, and even though they were from two different data sources, the fact that they had these inflection points at basically the exact same time, it shows that there's a pattern here, and maybe we could trust it. Also, we just wanted to mention that the reasons why this could possibly happen is because the mother, she might not want to, like her body might not want to put so much effort into growing this placenta, when it's about to be excreted anyway. And another theory that we had, as mentioned before, was that the baby might not need the placenta as much at around month 7 since it's almost fully developed. So maybe there is a factor that makes it so the placenta doesn't have to grow as much because the baby isn't as reliant on it.
Also, in terms of the fetus, the graph that shows its growth rate, we noticed a inflection point around month 9, which we already mentioned, and this is where the growth rate decreases, which makes sense because around month 9 is when the baby is born, and once it's born, it's going to focus on breathing and eating and other things other than growing, so this growth rate is going to decrease.
This concludes our project. Thank you, Dr. Gonalvi, for a great year.
Thank you.
You were real.